Good day, Math 30-1s. Today we are moving on and talking about solving radical equations after a conversation about transformations and square rooting an entire function. Solving radical equations was first introduced last year in 20-1 as an algebraic process. We're still going to solve algebraically, but the new approach is to talk about things graphically. So we haven't really approached things graphically. But in Math 30-1, we're doing a lot of function transformations, and so graphical approaches are much more inherent. So if I were to ask you to solve the square root of x plus 5 equals 0, many people would guess and check to say, what is the value of x that makes this statement true? And a lot of you could say, well, if I put a negative 5 there, it's a negative 5 plus 5 that is a 0, and the square root of 0 is in fact a 0. And that is a correct answer. We approach things a little bit differently by doing opposite operations though. Last year I would have told my students that there are 3 steps for solving a single radical equation. First step would be to isolate a radical. At this point it is very, very convenient to square both sides. What this would do is this would cancel out the radical, and then you're not dealing with a radical equation, and you'd be left with a quadratic or a linear equation, and you'd basically solve whatever type of equation you have. So that could be linear, that could be quadratic, and it could be messy. So isolate a radical, done. Square both sides. Solve for x. We can subtract a 5 over, and that is what we get. Let's actually travel straight down to the bottom here and approach this graphically. What is it asking when it says, when is the square root of x plus 5 equal to 0 graphically? When does the square root of x plus 5 equal 0? This is actually referring to 2 very separate functions and asking when do they meet. When does y equal x plus 5 rooted equal y equals 0? When do these meet? Now the very top one is a square root of x that has shifted 5 to the left. Think of this plus 5 as an x minus negative h. This is a 5 to the left of a radical function. Think about y equals 0 as a linear function traveling right along the x-axis. Y equals 0. Big question is, when do these meet? When do these intersect? And of course, they intersect at x equals negative 5. So graphically, we're actually asking about when do 2 functions meet? When do they intersect? The good thing about graphical solutions is they don't actually lie, and they will always sort of give you a true answer. But there are, again, issues if you're using a graphing calculator. Well, it won't always give you an exact answer. So how about a case like 2 times the square root of 3x minus 2 minus a 4? When does that equal 0? Well, if we were to approach this last year, we would use opposite operations and solve for x. It's a little bit challenging to guess and check this one. So let's start with some opposite operations and add a 4 to the right side. We could divide both sides by 2. And now, isolated radical, we can square both sides. If we add a 2 over to this side, we can divide both sides by a 3, and x equals 2 works. Now, it is actually quite important to check your work, because we do want to make sure that we're not making any issues. It is with that comment that we're going to talk now about checking your answers, just to make sure that we're not dealing with extraneous roots that we did start to see last year. When we are solving algebraically, there are potential issues that can result. So when we're solving a question like, when is the square root of x plus 5 going to equal an x plus 3, if we were to do this algebraically, we would square both sides. Now there's enough of a challenge in this question. When you see the x plus 3 squared, many people would forget that this is actually x plus 3 times itself. So I'm going to rewrite that a little bit differently, just so that we see why it's actually x squared plus 3x plus 3x plus 9. So when we expand the right side and distribute, we have a quadratic that appears. We can move everything over to one side so that we have a positive x squared term. And conveniently in this example, we have something that's factorable. An x squared plus a 5x plus a 4. Now without going through a lesson on factoring, this does factor very nicely into an x plus 4, x plus 1, which gives us two solutions, an x equals -4 and a -1. But before I box that up, I'm a little bit unsure, and I do need to check my work algebraically like we should have on the previous page. So let's take each of these and plug them back into the original example to check to see if this actually works. I'll start with -1. The square root of x plus 5 should equal x plus 3. We have the square root of 4 should equal 2. And in fact, 2 does equal 2. Let's check x equals -4. The square root of x plus 5 is supposed to equal x plus 3. I already see a little bit of an issue on the right side. There's a square root that equals a -1. And I already know that a square root cannot equal a -1. But it does say the square root of 1 equals -1, and 1 does not equal a -1. At this point, a few people might say, but isn't the square root a positive or negative? And this is a bit of a side conversation, but it's an important one, that according to something called the square root principle, the square root of 9 is only a positive 3. If I were to ask, when is x squared equal to 9? That's when you have a positive or negative that results. So if you're square rooting with variables included, you are dealing with a positive and negative result. But if you're dealing with only a square root of a number, an expression to evaluate, you only have the positive that results. And this is called the square root principle. So in this case, the square root of 1 does not equal -1. Graphically, this gives us a little bit more confidence that we're doing a correct result. So let's sketch again both of these functions, the square root of x plus 5, and ask, when does this equal x plus 3? Now my grid is a little bit off, but we do have to travel 1, 2, 3, 4, 5 to the left and draw our square root function. We'll do this accurately this time. So we travel with our base function, 1 right, 1 up. 1, 2, 3, 4 over, 2 up. The square root of 4 is 2. 1, 2, 3, 4, 5, 6, 7, 8, 9. The square root of 9 is 3. The square root of 10, 11, 12, 13, 14, 15, 16. The square root of 16 is a 4. This is the square root of x plus 5. We can sketch x plus 3 as a linear function with a y-intercept of 3 and a slope of 1. And already I can see where that intersection takes place, at the x value of -1. So the only answer is x equals -1. We'll be clear to scratch off the -4 and say it's not a solution, it's extraneous. And as a bit of a side conversation, why did it say -4? Well, technically, if this graph did continue with a negative side, it would intersect, if this existed, it would intersect at an x value of -4. But this bottom half of the graph doesn't exist because I didn't say sketch the positive and negative version of x plus 5. I said just sketch x plus 5 square rooted. So this part of the graph doesn't get to exist, and so therefore there isn't a solution on the negative side of the x-axis. occasionally questions will get a little bit more complicated, where if we solve them algebraically, we have to be a bit careful. So there's one that you can pause the video and try if you like. Otherwise, I'll continue. And there is an example 3 below, which will result in a quadratic formula. So we'll take our time with that one. For the very, very top one, we'll approach it similarly and square both sides. When you square the x plus 2, a similar x squared, 2x, 2x, and a 4 results. And if you move everything over this time to the left side, so our x squared term is positive, we have an x squared minus a 4x minus a 5, that equals 0. And as we factor, we have an x minus 5, an x plus 1, that equals 0, giving us two answers, a 5 and a negative 1. And if you do struggle with factoring, again, you can visit mrlemko.ca, and under Math 10C, there is a video about how to factor. Both of these would actually check if you plug them in, and so I'll save that as an exercise if you like to do, but these both would in fact work. But you would plug in a 5 into both sides, plug in the negative 1 into both sides, and evaluate each to ensure they work. For example 3, this question asks in simplest exact form, and sometimes that's a very huge hint to say it might not be okay to leave things as a decimal. So if we square both sides, we result in a similar x squared, 2x, and a 1, and expanding to occur. Moving everything over to the left side, 3x squared minus x squared minus a 2x minus a 2. We end up with a 2 factored out, and unfortunately all of our factoring skill can still not make this possible. So we might ask, does this even work? Maybe in your graphing calculator you punch in y1, y2, and you see if there's actually an answer. As a good hint, your graphing calculator will actually never lie to you and will not even give you extraneous roots. It is limited in giving decimal answers, but this will tell you whether there is actually an answer or not. But just because this does not factor does not mean there's no solution. It might mean there's decimal answers or irrational answers. So the quadratic formula says that we have an a value, a b value, and a c value that goes into a formula. So the quadratic formula is on your formula sheet in Math 30-1, but we have a negative b plus or minus a b squared minus 4ac, all divided by a 2a. So we plug in our negative of negative 1, and we squared our our b squared, negative 1 squared is a 1, minus a 4ac, all divided by a 2 times a 1. We end up with a 1 plus or minus a 1 minus a negative 4. I do see two negatives, so this is a 1 plus a 4, that is a 5, divided by a 2. These are your two answers, which again we should check, but if you are graphing this first and you do see two intersections, we know these are the two answers. And the last question to discuss is, again graphically, but in a bit of a unique way. This is asking us to solve an equation graphically in our calculator, answering to the nearest tenth. And so this is one for you to try. There's a y1, there's a y2, and this one is very much pushing the buttons, second trace. As long as you can see both intersections, it'll work, but a second trace, number 5, intersect, and then you're enter, enter, enter. So you press enter 3 times, and you should have your answer to the nearest tenth. Now, the very last one is a little bit unique. This is what it would maybe call a conceptual or a problem-solving question, as it says the solution to the equation could be achieved by equating which two functions together. So I've already said that you could take y1 and y2 and make them intersect. That doesn't really look like it's any great options. What you can do with equations, though, is rearrange them. I could say, let's take that square root of x plus 2, and let's actually subtract a 3 over to the left side. It would look like this. I could now say, when does the square root of x plus 2 minus 3, option 1, intersect with y equals x, which is option 4. So I could say 1 and 4 would produce the same result. Is there anything else we could rearrange to produce a solution? So again, let's try to rearrange more things. What if we move everything over to the left side and get the square root of x plus 2 minus a 3 minus an x and say equals 0? That's actually giving us option 5 intersecting with option 3. Are there any other possible answers? Unfortunately, those are the only two. With that in mind, that is the end of Chapter 2. After transformations, square rooting functions, and solving radical equations, all that's left is a little bit of practice.